Welcome to third in the series of videos on electromagnetism. In the previous video, we saw the effect of a current carrying conductor, a straight current carrying conductor, and how the magnetic field is produced. And we also looked at the magnetic field of a solenoid, which was more or less equal or similar to that of your bar magnet. In this video, we're going to combine both these concepts and try to find out the magnetic field lines of a coil. So if you have a coil like this, then how would the magnetic field lines be? So we're going to deduce from what we have learned in the previous two videos. So this is a setup which passes your current, and the current is passing through the coil, and it comes through here. So the coil can be something very similar to what you have seen here. So you go here. So you can see that around this coil, these magnetic field, this compass is moving around this line. So you can expect something very similar over the section of wire. So you will see that the magnetic field lines are moving in circles, right? And you can find that by your right hand thumb rule, which is you keep your thumb in the direction of the current and the fingers curl in the direction of the magnetic field, which is this B. And you can see in this, the thumb is in the downward direction, in the direction of the current, and the fingers curl. The B fingers represent the direction of B. So I can draw this, concentric circles, and then I know that the direction of B would be like this, right? And you can see that in the center, both these sides add up in the center. So the B on the magnetic field on both these lines add up. So in the center, if you really focus on the center, what you will find is that the field lines are going in. So that can be shown in this. So you can see that in the center, on one side, you have the compass pointing inward, and on the other side, you can see that the tail is pointing towards the other side. And on one side, you can see that the head is pointing to the other side. Now, this is something, you can see that this is not the case. Effect is exactly due to the current. You can see that. There. I switch it on. There you go. The magnetic compass is active and it is pointing towards the center. And as you come out, the tail is pointing towards the other end, right? So let's analyze this and see how to show this. So if you have, and this is very similar to a solenoid. So in a solenoid, you have a number of coils which is passing current, and your north is here and south is here, right? Here you curl your fingers. So here your finger represents the current in the right hand, and your thumb shows the direction of the magnetic field. So this is your B, and that's your thumb, right? Now you imagine that this is only one coil. Now if you have only one coil, and then this side is still north and this side is still south. Now as you're seeing from here, this one coil, it acts as if you are the current is moving. When you see from here, this is view one. The loop looks like this, and you see that this side is the south, right? And the opposite side, the side facing the other side, which you don't see, that will be the north. So invisible side is the north. Now as you see from here, which is view 2, then you will see that your diagram would be more like this. So you will see your current is moving in this direction, right? And this side will be north. So people remember this by putting an arrow like this, and this arrow and this arrow will align. And here you will see that this arrow and this arrow will align. So what this says is basically, depending upon which side you're looking at, it will be either south or north, depending upon the current is moving anti-clockwise or clockwise. So if it's moving clockwise, it's south from where you're seeing, and if it is moving anti-clockwise, then it's north from the side you're seeing. So I hope you enjoyed this video. See you in the next one.